guys, Miss Stanton here. I just want to go over some notes for Unit 2, Section 1, which is Modeling Distributions of Data. So we're going to describe a location and distribution in Section 1, and in Section 2 we'll learn more about normal distributions. So we'll talk about percentiles. We already spoke about those when we did box plots. But in general, a percentile of a distribution is just the value when that percentage of observations are less than the number you're interested in, right? 25th percentile, that means 25% of the values are below the value you want. So here's an example. It says Jenny earned a score of 86 on her test. How did she perform relative to the rest of the class? So you have to find where the score of 86 is, and she scored greater than 21 out of the 25 observations. So she would be in the 84th percentile, meaning that 84% of the scores are below hers. So with cumulative relative frequency graph, you made one on worksheet 1.3, but just a quick review. You have your frequency for each range or each bin, right? Your relative frequency, and remember the word relative just means you're going to make it into a percentage. So there were 44 presidents here. We obviously did our worksheet 1.3 with more current data, but on this there were 44 presidents. So it's divided by 44, right? 2 of them were in the age range of 40 to 44 inauguration, 7 were 45 to 49, and so on. Cumulative frequency means you keep adding the frequency as you go. So 40 to 44, there were 2 presidents inaugurated at that age, right? 45 to 49, it's 2 plus 7, which is 9 presidents. So it's basically how many presidents were that age or under, right? It's cumulative. And of course, cumulative relative frequency is going to make it into percentages. So you would divide cumulative frequency by 44. And you can put it on a graph, right? And this will be called the cumulative relative frequency graphs. Cumulative because it accumulates until it gets to 100%. Relative because you're using percentages, right? And frequency is because we use frequencies. So here's this graph, and you guys made this graph on worksheet 1.3. So this is just a matter of how to interpret, right? How to interpret this kind of graph. So it says, was Barack Obama, who was inaugurated at age 47, unusually young? So you have to kind of look and see. Okay, so he was in 11th percentile, so that is young. He was one of the younger presidents, right? Next it says estimate and interpret 65th percentile. So you're going to go to 65th percentile, right? And you're going to see what age at inauguration that corresponds with, and that corresponds with 58 years old at inauguration. So that means 65% of the presidents for this data set, which stopped at, again, it's not the most current data, right? But it means that 65% of the presidents at 65% of presidents at inauguration were 58 or younger. Now we can also measure a position using something called a z-score. And a z-score has a very specific formula. It's called a standardized value. And what you are doing is just finding out how many standard deviations from the mean the observation of interest is, right? That's what Z is. How many standard deviations above or below the mean is the observation you're interested in. So you have to take your value you're interested in minus the mean of the distribution divided by standard deviation. And that makes what we call a Z-score. Now, if Jenny earned a score of 86 on the test and the class average was 80, the class mean is 80, and a standard deviation of 6.07, what is her standardized score? So using this computation, you're just going to do the value of her test minus the mean divided by standard deviation, and that will give you the z-score for how many standard deviations her score is above the mean. Using z-scores for comparison works well, just because here's the situation, right? Janie earned 86 on the stat test. Class average was 80, standard deviation was 6.07. She earned a score of 82 on her chemistry test. So if you go just by scores and look at 82 and 86, right, seems like she did worse on the chemistry test. The chemistry scores had a fairly symmetric distribution with a mean of 76, so the class average on the test was lower, and a standard deviation of 4, but the standard deviation was lower as well. On which test did Jenny perform better relative to the rest of the class? So we're going to find our z-score for both tests, right? For the stat test, she really is a z-score of 0.99, so that's almost 1 standard deviation above the mean. And for the chemistry test, her z-score is 1.5, which is 1.5 standard deviation above the mean. So if you're comparing these two scores, you have to say that comparative to her peers, relative to the rest of the class, her performance was better on the chemistry test, even though she received a lower score. So when we transform data by adding or subtracting a constant, so if you have a set of data for a variable, and you want to add the same value to every number in that data set, or take away the same value from every number in that data set, that would be one of the ways you can transform a variable. And adding the same number, a positive or a 0 or a negative number, to each observation is going to add that value to the location of the center, mean or the median, right? It's going to add that value to the quartiles, but it will not change the shape of the distribution, and it will not change the measures of spread. So the IQR will be the same value, standard deviation will be the same value. You didn't change the shape of the data, right? You just kind of shifted it on a number line, either up or down. So it changes things like location-based things like center, right? Max, min, median, quartiles, but it does not change the shape of a distribution. Here's an example, right? You just shifted the data up by adding a constant. Now, another way we can transform data is by multiplying or dividing by a constant. Like, for example, if your data set was in inches and you wanted to change it to feet, or if it was in yards and you wanted to change it to feet. If it was in centimeters and you want to change it to millimeters, right? If you have to multiply every number by a constant, or divide for that matter, right? You're going to have to multiply the measure of the center by the same value, and the measure of spread is going to be affected as well by multiplying by the absolute value of that number. But the shape of the distribution is going to stay the same. So here's an example, right? The basic shape is the same, more spread out, but still has kind of two modes, right? And now we'll talk density curves, which actually will bring us to a very important thing we learned, normal curves. But we'll talk about density curves in general here. So we know how to describe the distribution. We use SOCS to describe the distribution of quantitative variables, right? We plot it, we look at the graph, we look for our SOCS, right? Shape, center, spread, outliers, all those things. And we always do it in context. We do our numerical summary, right? Describe the center correctly. We know to do all these things, right? But sometimes the overall pattern, if you have a very large number of observations, right, is so regular, we can describe it by a curve. So here's going to be an example, right? So it's like a histogram of observations here, and then you kind of lay a curve on that histogram, and that is what we call a density curve. Now, density curve always on or above a horizontal axis and always has an area of exactly 1 underneath it, meaning that 100% of the observations are below it, are under it, right? It covers all the observations. So the overall pattern, when you look at this histogram, right, it's scores from 947 7th graders in Gary, Indiana on the vocabulary part of a standardized test, right? We're describing it by a smooth curve, and that's what we would call a density curve. So when we talk about describing density curve, if you talk about the median and the mean here, the median is the equal areas point, meaning that 50% of the data should fit above the median and 50% of the data should fit below the median. And the mean is a balance point. So the median and the mean, when the distribution is symmetric, right, are going to be the same or very close, because no distribution is perfectly symmetric. But if it is a symmetric, or if we're modeling something with a symmetric distribution like a normal curve, the mean and the median would be the same. But if your distribution is skewed, the mean is always going to be pulled in the direction of the skew or the tail. For example, this here is skewed to the right, so the mean is going to be higher than the median. When the distribution is symmetric, the mean and the median are the same value. And remember, the median tells you where the equal areas point is. Oh, 50% of the data is going to be below that value, 50% above, whereas a mean is the balance point of the curve. And that brings us to the end of section 1. Next, we'll talk about normal distribution.